And precision on some of these atomic particles are like that of a proton or a neutron. Calculations show, you vary a proton, the mass of a proton by 1 part of 1,000, we're not going to have atoms, folks. How did protons just happen to have the right mass? And the neutrons have to have the same relation. I mean, it's the same situation with neutrons, per se. How did this just happen? Things that we normally take for granted. Hey, this matter is very complex and very precise. One of the things that has very much influenced the scientific community, although they have not accepted it as evidence for God per se, is the forces of physics. This has been going on for the last 20 years. That, these things, how come they're so precise in their quantity and so useful in the area in which they work? Things have to be exactly right, or the whole universe falls apart. Our whole universe made of atoms falls apart. Well, we have 4 main forces in physics right now, anyway, unless you want to go into string theory. And I'm not going there tonight. Some people say string theory is fit to be tied. And, anyway, strong nuclear force. If it were 2% stronger, we'd have no hydrogen. That's pretty disastrous to our universe, as you may know. Slightly weaker, we'd have only hydrogen. Boy, everything would be very boring if you only had hydrogen atoms around. I mean, it's just, very, very close precision there. The weak nuclear force, for slightly stronger, helium would not form in the sun. And we need that in order to get the energy from the sun. If it was slightly weaker, no hydrogen would be left in the sun, and well, that'd be too bad for us, because that's where our energy comes from, type of thing. So you get a little bit of an idea of how these things work like that. The electromagnetic force, if it were slightly stronger, the sun would be a cool red star, and our temperature wouldn't be suitable for life here. Slightly weaker, it'd be a hot blue star, and probably would have burned itself out a long time ago. Gravity, much weaker than these other forces. And I'm going to point out, these forces work in certain specific areas, and so fortunate. It's so fortunate that a strong nuclear force works in the nucleus. Because if it worked beyond the nucleus, we'd all collapse, folks. I'm sure glad it stays there. The electromagnetic force, extremely important in connection with chemical changes and the production of light that we mentioned, for instance, and so on, involved in that type of thing. Gravity, very much weaker than these other forces. Only 1 part out of 10 to the 39th power. Yet it's so extremely useful. I mean, gravity keeps the water in the oceans, isn't that nice? It keeps galaxies together. Keeps our planets going around the solar system and so on, as Newton so elegantly described and so on. And so we got these very interesting and precise forces out there doing various things of the right strength so that we can have a livable universe, so that we can exist as people. And so on, because we're made up of these atoms and so on. Well, the last 2 forces I mentioned, the electromagnetic force and the force of gravity, have a very close relationship. Extremely precise relationship is necessary for them to work properly in the sun. And the sun, is our source of energy, type of thing. How close is that relationship? It is, in terms of strength, if either one of those varied by 1 part out of 10 to the 40th power, you would not have atoms as we have them. What is one, I mean, this is extremely precise energy relationship that you have. And I've written the number out here. It's one, there's one here written out there with your 40 zeros after that. Well, you know, we tend to lose our ability to envision these things. You know, you start talking about trillions in the national debt and so on, and you know, you're just beginning there down your numbers of zeros when you're starting about trillions. How close is this relationship? Let me give you an example. Supposing we had a pile of matches, okay? Matchsticks. You got a pile of matchsticks here. And this is a spherical mass, we'll say, because we're out in the universe here. And it's much bigger than the Earth. In fact, it's not only 1,000,000 times bigger than the Earth, it is 1,000,000 times bigger than the Earth. That mass of matches, or matchsticks, we should use that term, mass of matchsticks, would just fit between the Earth and the Sun. So it's a lot of matches. If you could fly by commercial jet between the Earth and the Sun, it'd take you 19 years of constant flight to get there. And you're investing a lot of matches when you're doing that. If you could fly through the matches, of course. There's a greater chance that gravity or the electromagnetic force could have the right value than of you being able to find the right match in that pile of matches. Supposing we're real cold and there's only one match in that whole pile of matchsticks that has a head on it, okay? Close your eyes, and here you're in this pile of matches between here and the Sun. There's a greater chance that gravity would have the right force as it relates to the electromagnetic force. Then you would pick the right match out of that great pile between here and the Sun. But with a little bit of an idea of how improbable it is that some of these forces have the right strength, per se, so that atoms can exist. How could all that, pretty like some of these people suggest, it would take just a tremendous amount of good luck after good luck after good luck for this to happen. And when you run into such improbabilities, it's time to start looking for some other paradigms or answers.